Okay, so here I'm going to work out with you a problem from Serway. It's chapter 25, number 7, and it's involving electric potential. So let's just read it. An electron moving parallel to the x-axis has an initial speed of 3.7 times 10 to the 6 meters per second at the origin. Its speed is reduced to 1.4 times 10 to the 5 meters per second at the point x equals 2 centimeters. Part A, calculate the electric potential difference between the origin and that point. Part B is which point is at the higher potential. And then I'm adding a part C here, which is not in the original textbook, which says that assuming the region of space has a uniform electric field, determine its magnitude and direction. Whenever we're approaching a physics problem, we should approach it systematically. So I've added some steps that I'd like you to try to use whenever you're solving physics problems. Even though you might be able to take some shortcuts and do this in your head, if you get in the habit of using these steps, you'll be in better shape when it comes to more difficult problems and problems that you might see on exams. So I know this feels like a slow process when you're starting out, but the more you practice it, the faster you'll get at it and the better off you'll be when you come to harder problems. So here are the 6 steps here you can see. Let's try to go through these steps one at a time in solving this problem. So let's start with the first step, which is to conceptualize the problem. This is processing the information that is in the problem in order to get our heads around what's going on. What information is given, what is being asked for, and once we've identified that, we should draw a careful sketch or picture of the problem and to write down what we know and what we're looking for. Getting this information in front of you will help you in the problem-solving process. So why don't you go ahead and stop the video now and see if you can process what is being asked for, what is given, and see if you can draw a picture of the problem in order to get started. One of the first things I like to do when I'm processing the information in a problem is to circle the things which I think are important. So I've circled in green things that we should pay attention to. The electron's moving parallel to the x-axis. We have an initial speed of 3.7 times 10 to the 6 meters a second at the origin. And we have a final speed at the point x equals 2 centimeters. One other thing we should pay attention to is remember that this is an electron. So that's one crucial piece of information. For that, we know the mass of the electron and the charge of the electron is going to be minus E. These things are known. And then I've also put in a red box what we're trying to find. So calculate the electric potential difference between these 2 points. That's our target variable. So now let's use this information to represent the problem graphically. So I'm going to draw the electron at the 2 relevant times, initial and final. And I'm going to give all of the relevant information with variables. So I've got an initial time with speed VA and a final time with speed VB. The initial position is XA and the final position is XB. So remember that you're going to want to include a coordinate system so we know which direction is positive. We're going to choose this direction to be plus X. And now what we're trying to find is the electric potential difference. So we should note that the point initially here has electric potential VA, capital VA, and the final point here has electric potential VB. And our target variable is going to be delta V. We want the electric potential difference, which is VB minus VA. Now that we have a clear idea of what's going on in the problem, it's time for the second step. What are the main physics principles you should use to solve this problem? So why don't you stop the video right now and see if you can start planning out your solution. What are the physics ingredients that you need in order to get going on this problem? Now we need to think about what equations we can use to get started on this problem. We're looking for the electric potential difference, so there's a couple equations that I can think of that involve this quantity. One is delta U is equal to Q delta V. That's the fundamental definition of electric potential energy and relating it to electric potential. The second place delta V shows up is in delta V is equal to minus E dotted with delta X, which is for a uniform electric field. Both of those have our target variable in them. Which one of these is better? Well, they both have things we don't know in them. For example, we don't know delta U, the change in electric potential energy, and we also don't know E, the electric field. So which one of these should we use? One giveaway is that part C is asking for the electric field, so unless we solve the problem out of order, we're not going to be able to use number 2 until we've done part C. The other thing to think about is that electric potential energy is something we can access because we have information about the speeds of the particles at those 2 times, so that means we can relate that to energy. So we're sort of starting to form a problem-solving strategy here that we're going to use energy in order to access delta U, and then from there we can get our target variable delta V. So now that we've identified that some of the important information in the problem involves energy, can you try to make it a bit more fleshed out? So can you write down a detailed plan about how you're going to solve this problem, including the important equations? So why don't you stop the video right now and give it a try. Try to set up the problem and even go ahead and start solving it if you think you're able to. So we've sort of identified an energy approach to solve this problem. We want to use conservation of energy, so we're going to use conservation of energy, and our starting point for that is always going to be delta K plus delta U is equal to 0. And then of course we need to substitute in here delta U is equal to Q delta V. Delta V of course is our target variable, so we need to substitute that into here. And then the kinetic energy, of course, delta K is K final minus K initial, with kinetic energy equal to 1/2 mv squared. And we're going to substitute that in here. So our plan is to start with conservation of energy, make those substitutions, and then solve for delta V. So we have a sort of 2 or 3 step plan. 1, 2, make these substitutions, and then 3, solve for V. Now that we have a solid plan for how to solve the problem, go ahead and stop the video and see if you can execute that plan. So go ahead and see if you can solve the problem yourself before you continue. So now I'll just go ahead and execute that plan. So we're going to, for delta K, we're going to put in 1/2 mv final squared minus 1/2 mv initial squared. That's final kinetic energy minus initial kinetic energy, plus delta U, I'm putting in Q delta V equals to 0. Now the trick here, you have to remember that Q for the electron is minus E. E is a positive number. So I'll make that substitution also. 1/2 mvf squared minus 1/2 mvi squared minus E delta V is equal to 0. And now let's solve for delta V. So we'll bring this last term over onto the other side. 1/2 mvf squared minus 1/2 mvi squared is equal to E delta V. And finally, I'll divide by the E and also pull out the 1/2 m just to make it a little bit easier to read. 1/2 m over E, Vf squared minus Vi squared is equal to delta V. So we have now an algebraic formula for our target variable delta V. We're ready for step 5, which is to plug in the numbers. So all we need to do now is plug in all of the numbers. Everything on the left side we know. So why don't you pause the video and go ahead and do that step yourself. So I've gone ahead and done that. Put in the mass of the electron, the charge of the electron, and those 2 speeds. Before I jump straight to my calculator, let's start moving on to the next step, which is to do some checks before we rush to the calculator. The first and most important thing we should check is the units. So the units of an electric potential difference, delta V, should be volts. And remember, a volt is a joule per coulomb. If you don't remember what that is, a joule is a kilogram meter squared per second squared, and then divided by a coulomb. So our answer should have units of kilograms meters squared per second squared times coulomb. So now let's check and look at the formula. We've got a kilogram on the top, which matches that kilogram. We've got a coulomb on the bottom, which matches that coulomb. The two terms in parentheses have the same units, which is good. Anytime you add or subtract two things, they have to have the same units. And the units of that are meters per second squared. So it matches our meters squared and our seconds squared. So the units are okay. So then you can jump to your calculator, and I find the answer. The answer for delta V is minus 38.87 volts. So there's the answer to part A. Let's move on to part B. Which point is at a higher potential? This is really conceptual because we don't need to do any additional work here. We've already solved for delta V, and notice that delta V is VB minus VA, and we have that as being a negative number. So therefore, VB minus VA is less than 0, which means that VA is bigger than VB. Does this make sense? Let's think about what this means. Remember, electric potential is kind of like height. So the one that's higher is uphill compared to the other one. We're learning that VA is uphill compared to B. This is downhill. So VA is at a higher potential than VB. Let's think if this makes any sense. Remember, if you have a normal ball and it rolls downhill, it gains kinetic energy and loses potential energy. I like to remember that positive charges behave like the ball rolling down the hill. A positive charge, as it goes downhill, gains kinetic energy, loses potential energy. But electrons and negatively charged particles are weird, so they behave the opposite way. Electrons gain kinetic energy when they roll uphill, and they lose kinetic energy when they go downhill. So this electron here is going uphill to downhill, should lose kinetic energy. That's how an electron behaves. And that's exactly how this electron behaves, because it slows down. It starts off with a faster speed and then moves to a slower speed as it gets to point B. So it's an electron, it's gone downhill and it's lost kinetic energy. That makes sense. It agrees with our calculation. So it makes sense. Electrons lose kinetic energy as they go downhill from high to low potential, high V to low V. So this is a good check on our calculation. Okay, so let's move to part C now. Assuming the region of space has a uniform electric field, determine its magnitude and direction. So we've got a new target variable, which is the magnitude of the electric field and the direction of the electric field. So before you go further, see if you can pause the video and see if you can get started on this yourself. So the first thing we can do is start thinking about the direction of the electric field. We've done everything we can with energy, so we have to start thinking in a different way now. The direction is conceptual, so let's think about, there's a couple ways we can think about the direction. One way is to remember if you have the electric potential energy, or the electric potential, sorry, you know that the electric field points from uphill to downhill. So the electric field points downhill. So we already know, since we know that point A is higher potential than B, my electric field should be pointing to the right. Another way to think about it is to go to a free body diagram of the electron somewhere in the middle there. Clearly it has a force pointing to the left, right? Because it's slowing down. So its speed is to the right, the force must be to the left. But then remember that F is equal to QE. Right? And for an electron, Q is equal to minus E times E. So you see here that there's a minus sign, meaning that F and E are in opposite directions, meaning my electric field should be pointing to the right, which agrees with our previous reasoning. So the direction of E points to the right. So now finally, to get the magnitude of the electric field, we need to use some physics, some formulas. We need to relate electric field to the things we've already solved for and the things given in the problem. We've already used the speeds, but we haven't used the distances yet. So we need to relate the electric field to the distances, which we haven't yet used, and also this delta V electric potential difference, which we solved for previously. So the equation which does that I mentioned previously is delta V is equal to minus E dotted with delta X. Delta X is a displacement vector going from point A to point B, so delta X is this vector. And we know the electric field also points in this direction, which we figured out last time. So we're going to use that formula. The only thing to be careful of is you have to worry about this dot product. Remember that the dot product of two vectors, A dotted with B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between those two vectors. So in this case, delta V is going to be minus the magnitude of E times the magnitude of delta X times the cosine of the angle between those two vectors. And what is the magnitude between those two vectors, or the angle between those two vectors? Well, they're both pointing to the right. Delta X points this way, and E also points this way. So theta is going to be 0 degrees in this case. So we have our plan. So now we just need to go ahead and execute the plan and solve for the magnitude. So now let's execute the plan. Let's go ahead and solve for our target, which is the magnitude delta E. So I just have to put everything else on the other side. E, there's a minus sign, delta V, divided by delta X, the magnitude of that displacement vector times the cosine of theta. Now delta V we know, minus, and then we have another minus 38.87 volts. And then in the bottom we've got delta X, that's the magnitude of the vector going from point A to point B, so that's 2 centimeters, 0.02 meters, times the cosine of theta, and we said that theta was 0 degrees because delta X was pointing to the right, and E was also pointing to the right. So here we have theta equal to 0. So now let's plug in the numbers. I get 1943.5 volts per meter for my magnitude of my electric field. Finally, let's do some checking. So there's a couple things we can check. One is the units and one is the sign. You might want to remember that the units of electric field are Newton per Coulomb. So that's kilograms, meters per second squared per Coulomb, or kilograms, meters per Coulomb second squared. And we can check that a volt per meter, remember a volt is a kilograms, meters squared per second squared per Coulomb, times 1 over meter. That's a volt per meter, so that's a kilogram meter per second squared per Coulomb. And these two match, so it has the right units for electric field, which is good. The other thing you can do is check the sign. Notice that the sign here came out positive, and that's good because this is the magnitude of a vector, right? We solve for the magnitude of the electric field. The magnitude of an electric field vector, or the magnitude of any vector, the magnitude is always positive. So that's good. came out positive, and it should be positive. So the sign looks good, the units looks good, and so we can have confidence in our answer. So finally, for part C, our answer is going to be that the electric field E, maybe I can put it here, is 1943.5 volts per meter, pointing to the right. There's our final answer, part C. So I hope you found this problem useful. I really urge you to go through these steps whenever you're solving any physics problem.